And before we are starting, I was just willing to say that we are going to cheer. We didn't find really the place to cheer, so we have put the chairs over here. This session together with Jan Bernstein, who is actually one of the top experts in gastric cancer, and he has been working for long with Peter Mauftener, and currently he is in Oxford. Yes, is it right? So I'm indeed happy that Jan had the possibility to come over here. And some of the people are still signing some contracts with the university and with the rector, but I hope they are also joining, and I'm happy for all of those that are here at the moment already. And maybe Jan, would you like to say anything?
Well, yeah, from me also a very warm welcome. I'm very happy we are here. I hope we have a bit of a lively discussion later, because this is also what these meetings are about, not only to present but also get into the exchange. I would like to thank Marcis for organizing this, and all your team who have been very helpful and great with the information already in the last days. And I'm also generally very grateful to be back once more in Riga, in this very lovely city, in this wonderful winter weather. I'm not quite prepared with my clothes for that cold, but I think we will all have a kind of warm and heated discussions here, so that should be fine. So, thank you.
Yes. Actually, this is the first day this winter, probably the only one that we are going to have the temperature like this, so that is special arrangement for you. Okay, okay. So all right, so let's move ahead immediately. And actually, this today's session we have designed with the title "Unmet Needs in Gastric Cancer-Related Prevention Issues," and we are very happy to have really three of the first presentations that are the results of the surveys of physicians, survey of patients, and also the survey of healthy people. So I think we can just immediately go ahead with the first presentation by Evita Gashenko, who is an oncologist and a PhD student as well, but actually working as a medical oncologist, on the questionnaire that has been made to medical experts. And then I would suggest that we could have also the other two presentations, unless we do have immediate burning questions, and then probably discuss all those three in a line. But please feel free to move around to take another coffee or something back at the table and come back then.
Good afternoon. I wanted to thank all organizers for inviting me to speak here today. And my topic is gastric cancer prevention and screening. Do we need it? A little bit of the background. I wanted to put in the Maastricht fifth consensus guidelines, where I took out just a few quotes from there, just to set the idea behind the questionnaire. I wanted to mention that they are saying that the risk of developing gastric cancer can be reduced by employing eradication treatment, that eradication is needed in communities with high-risk gastric cancer. I will be talking about search and treat strategy, which is quoted to be reasonable in communities at high risk of gastric cancer and high-risk individuals for gastric cancer. So, which are these communities with high risk of gastric cancer? To answer this, there is a measurement defined age standardized incidence rate, where high risk regions are where this rate is about above 20, intermediate 10 to 20, and low below 10. There is a map where you can see all world, but I will show you numbers too, because, for example, where we live, Latvia is in the same color as, for example, Japan, and we know that risk is increased in Japan way more than in Latvia, and the same for women. And here are some numbers. What you need to remember here is that you need to add men plus women to get that number, and here you can see, for example, our region, we have the total number of 27 Japan, which sets us in the region of high risk. I put in some countries for comparison. For example, in Korea, you can just add the numbers and see how big the difference is. And for our guests, I tried to look up the numbers so they can check them too. About the screening programs, so far we have only in 2 countries, in Korea and Japan, and right now in Korea that's upper endoscopy as a screening method, and in Japan it's both upper endoscopy and X-ray series. So the aim of this project, part of the project, was to study specialist viewpoints in respect of gastric cancer prevention. And better? Okay. Okay. We designed a web-based questionnaire in 3 languages, English, Russian, and German, as you can see to your right, and it was distributed globally with the help of international organizations and professional societies. Here you can see I'm sorry? Here you can see all in this blue color are countries who responded and who sent at least 1 questionnaire. In totality, we had 886 responses from 75 countries worldwide. More keen to answer were male physicians. Median age was 47, and most of them were medical healthcare professionals. So, 2 responses. The first question we asked was regarding gastric cancer burden, and do participants think that it's a disappearing problem? As you can see, 80% said that it's not a disappearing problem worldwide. We asked, do they consider a population-based screening appropriate? And here in answers, majority, once again, 62% said that yes, they would think that population-based screening would be appropriate. I wanted to show in several regions the same answer to the same question, and here I wanted to point out, for example, Russia and Ukraine, where the dominant answer was yes for the screening. In Europe, we had quite a few answers that screening wouldn't be appropriate, which is understandable knowing that there are many countries with low incidence of gastric cancer. We tried to divide the answers based on the main area of expertise of all respondents, and here we can see that others, those who are mainly physicians and family doctors and oncologists, were more certain that screening is needed, whereas gastroenterologists partly said that it's not needed. About search and treat strategy, we asked, would it be a good strategy to decrease mortality in country? Here we could see that even though guidelines, as I showed in the beginning, were saying that it's a good method and we should imply it in the countries with high incidence of gastric cancer, positive answer to this question was, was only in 45% of cases, and I think large part of the respondents were not sure about this answer, which also raises few questions. Why? Once again, we divided in this answer, breaking it into the regions, and here I wanted to show that a lot of answers about not being sure if search and treat strategy is correct came from Europe. Asking a little bit more about the methods which we could imply in screening, we asked about upper endoscopy. As it could be expected, respondents said that this method is accurate enough, but at the same time it wouldn't be acceptable by patients or cost-effective or feasible in public screening. In this slide we asked about upper gastrointestinal X-ray series, and what I found interesting in this slide that is the second part about acceptability. It was interesting to me to see that so many physicians and doctors said that it wouldn't be acceptable by patients, even though this method is not invasive. Also, they were worried about accuracy about this method. We asked also about pepsinogen screening. Here we can see that majority of respondents said that no, this method is not to be used in gastric cancer screening right now, and 1/3 said that it could be used only in certain settings. Knowing that we are working with volatile markers, we asked also about breath testing to test if respondents have information about this method, and we got quite a lot positive answers, 27%, saying that they think that this method can be used in certain settings, and 25%, which I think is very high, saying that yes, that this method could be used in screening, even though we need more information. There is so far only one publication about H. pylori vaccine regarding trials that was held in China. So we formulated a question about H. pylori vaccine. Here answers were probably as we suppose them to be, that people are quite keen for H. pylori vaccine, knowing the burden of antibiotic use. This could be a quite good alternative, but of course more data is needed. And conclusions were that majority respondents agreed that gastric screening is needed in certain regions around the world. In general, attitude was quite well responding with guidelines, though not so much in case of search and treat strategy. We managed to acknowledge the advantages and disadvantages of two major screening methods implemented in Japan and Korea. And I wanted to take this opportunity to propose to take part in some international programs like EUREC and STOP project, which are working in gastric screening, gastric cancer screening area and gastric cancer prevention. And thank you for your attention.
Thank you, and if there are any burning questions, if not, then I'm really happy to invite our guest from representing the patient organization, that is Europe Colon organization. And Geoffrey, I'm very happy that you are here, and actually the reason why we do have a Europe Colon organization speaking on gastric related issues, I think that is what you are going to explain, so we are happy to see you.
Thank you very much indeed for inviting me. I'm unashamedly here not only to tell you what we're doing, but also to recruit. For any survey to be successful, as we've seen from the survey that we've already seen, we need participants. And as we know, there are relatively few patient organizations in Europe for gastric or esophageal cancer, and that's basically where we're coming from. Oops, I've killed it. Oh, no, I haven't. Sorry. So Europa Colon was started in 2004 in colorectal cancer, which is why we have the name we have today. We are having next week a strategy meeting, and it is very likely that as a result of the strategy meeting, our name will change. But it's possible for the immediate future we will work with two names, but certainly Europa Colon doesn't cover the gastric element, which we moved into in 2015. So to bridge the gap, we identified a new slogan, United Against Digestive Cancers, and we started initially with pancreatic cancer, and we've been supporting a number of initiatives, many of those have been growing exponentially with a very active and dynamic patient organization, not only in Europe, but also across the world with the World Pancreatic Cancer Coalition, which grew out of patient enthusiasm and patient dynamic. But in 2017, we moved into gastric, and that was really motivated by the ECHO, the European Cancer Organization, decision to do an essential requirements for quality cancer care on esophageal and gastric cancer. We had been previously involved the previous year in 2016 with the essential requirements for colorectal cancer. Both the colorectal and now the esophageal cancer essential requirements have been published, and I can certainly find that information for you if it would be helpful. But what we found before we started working with ECHO was that there was a very small organization in the Netherlands. There were a couple of esophageal organizations in the UK. There is one very small organization in Germany, and that was about it. There was almost no other support for patient organizations. And when Europa Colon started in 2004, the prognosis for colorectal cancer was probably about the same as it is for gastric or esophageal cancer now, with about 6 months to live if you were lucky. As we all know, this has changed dramatically with screening in place and a number of new dynamic treatments. Well, the dynamic treatments we hope are going to start coming in esophageal and gastric cancer as well. But the good news is that Europa Colon has in 26 countries has 43 groups. Most of them are focused on colorectal cancer, and we're moving slowly to get them to change and embrace the other digestive cancers as well. But this takes a time. Many of them are voluntary organizations. So I will deal with how we are trying to address that in digestive cancers later. But the priority for us in this year will be the survey. Basically because there is so little information available and so few patients that we can work with, we decided the best thing to do would be to undertake a survey, which I'm very pleased to say Marcus has been involved with, and Evita has very kindly helped with the translation into Latvian. My colleagues in some of the other countries are working with me. Cyprus, for example, where we've recruited the president of the European Cancer Oncology and Nurses Society, and they are across Europe working with us as well, are working as well to bring this to fruition. But we need more clinical support to assist with recruitment. What we're hoping for is 100 patients from each country completing the survey, which can be done online or can be downloaded from the the website and completed in hard copy and returned to an address either in their country or in the UK. We will be responsible for uploading the information. And as I said already, we are supported by the European Oncology Nurses Society. So we hope to launch recruitment in April 2018. I'm just finalizing the translations at the moment. The IT version is pretty close to finish in the UK version. Then I need to transfer everything so that we can get that ready for April. I didn't want to conflict with the European Colorectal Cancer Awareness Month, so we're launching the Digestive Cancer Survey or Gastric Esophageal Cancer Survey in April. I'm looking at local financial support to bring this about and to also recruit a local MSD or PhD student or even a nurse who would be interested to take on the project and be responsible for recruiting the 100 patients in their country. We have already somebody in Cyprus, we have somebody in Spain, and we are looking at somebody in Portugal as well. Whoever takes the project on board will be able to work with the local data and our local affiliate organization if one exists, but Europa Colon will ideally publish the European-wide data first. Which brings me to another point. As I said earlier, when Europa Colon was started, there were very few patient organizations, and I've alluded to there are very few digestive cancer organizations in Europe. We need to change that. We need to change it not only so that you can do more effective research, but also so that we can understand and support the patients and the carers who are challenged, particularly in gastric cancer, with a very short prognosis. So the aim is to start using a model that has been developed in a number of disease areas, a pilot, hopefully in 4 countries if I can get the income to do that, working alongside the local hospital to create the opportunity for patients and carers to meet on a weekly or bi-weekly basis, and so potentially grow new organizations out of that model. But as we all know, communications is absolutely key in today's environment. And what we hope to achieve with this heat map is the ability to be able to look at information and potentially work with other organizations who have got information that, for example, if we were to put our cursor on France and click on France, a number of indicators would come up which would indicate various clinical markers that would indicate numbers, statistics, hospitals where treatment was available. So information that would be available for a patient, information that would be available to compare your country with another country, but also the opportunity to discuss this with your local health ministries, with politicians and European politicians, in a hope that we can start to broaden the base and standardize the base of treatment for these patients across Europe. And as I say, the heat map is absolutely essential. If we are to bring patients up to speed, we need a tool for them to work with. And hopefully we will get to the stage when we have in Europe patient organizations in Europe who are as dynamic and as enthusiastic to make change as they are in the US. This is just to broadly set out some of the communications opportunities which will come from the heat map and the development of indicators. We are working with ECHO at the moment to develop indicators for the essential requirements for colorectal cancer, and I'm hopeful that once that has been sorted, we can identify indicators for esophageal and gastric cancer. I'm sure I don't need to tell you that one of the reasons why we're lumping esophageal and gastric cancer together in this patient survey is that the treatment and the experience is relatively similar. So we've been led to believe anyway. And as we've already discussed, we will discuss questions at the end, unless there are any burning questions. Thank you.
We slightly changed the plan because we realized that the next 3 talks are all on the sniff phone technology. So we would actually put these 2 talks together and invite for questions now. So Evita and Geoffrey, if you would come back to the front, and I invite any of the audience to ask questions. Thank you again for 2 outstanding talks and very, very much needed projects that are on their way there. So may I just ask with a question for you, how you said one of the aims is, and I think this is one of the most needed things, is to equalize care, to homogenize care across countries in Europe. How do you think you can achieve that? Because there's not only different standard of life, there's also different healthcare systems. Me, just coming back from Germany back to England, I realized that quite dramatically what differences there are. So
relatively good ones. As we know, the standard of care in Germany is better than it is in the UK, but as we look at the whole of Europe, the standard of care in those 2 countries is probably a lot better than most of Eastern Europe. So you highlighted just by that one statement the huge disparity that exists. And I think this is one of the opportunities that the ECHO Essential Requirements offers, that 25 societies came around the table and they discussed what the basic requirements or the essential requirements were that were needed for treatment at all levels. So right from diagnosis and pathology all the way through to palliative care. And I think that is one of the reasons why we're so enthusiastic to get to be working with ECHO on this, because we as a patient organization can only set a certain standard. We can't talk directly to clinicians in the same way that an organization and have the same gravitas that an organization such as ECHO would have. So hopefully those indicators and the ability to use that information at a policy level can start to get a discussion going which might lead to change. And even in colorectal cancer, after all these years, we still have huge differences in care. We have huge differences in screening, which this has been a European requirement since 2002. So we have a long way to go.
To follow on Jan's question, I think it's really important, but the reason why you're conducting the survey is to gather the information from the patient's perspective, right?
Yeah.
And across the European countries, and
well,
then
we've only got, at the moment we've got 10, or we've got 11, and we're hoping to have 13, but we unfortunately don't have money to cover every country.
But then that you will focus on then the patient's experiences, basically. So then, because there are two like different axes, like one from the patient's perspectives, but also like kind of from clinical perspective, like the standard.
We can't do both.
Yeah. So then you will start with the patients, and then you will use it for. You will use that information for
communication tools. Basically, if you searched patient experience or patient needs for gastric or esophageal cancer, you would find very little information on the internet.
Okay.
So the idea is to provide information. Masters has given some questions on Helicobacter pylori. There will be questions on health literacy. There will be questions about support. Who did you get your support from? There will be questions about chemotherapy, about pain. There's a limit to how big we can make the survey, which has been the problem with the survey we did in colorectal cancer. We included a number of EORTC questions, and it just became so burdensome that patients said,
sure.
So we've taken that out. Hopefully when we have a population of patients through the support groups, we can go back and do a different survey which gives more in-depth information, but we have to start somewhere. And so this is an attempt to create some markers that we could then use to communicate with the media, because breast cancer has changed over the last 10 years, mainly because there's been a very powerful lobby and there's been a media interest in the subject. Unfortunately, the other cancers, we don't have information, we don't have the lobbying group, and we don't really have the support of the media to make these cancers more attractive.
But I think it's very important, the work that you're currently doing. I actually had another question for her. I mean, it was an interesting presentation, but then I just wanted to ask you whether, I mean, from my understanding, there is actually no epidemiological evidence proving that the endoscopic screening or any type of gastric cancer screening is effective in reducing gastric cancer mortality. There is?
I think one or two papers just last
year
from the
last year
countries showing that you have mortality reduction.
But then is it from the randomized control trial? I didn't think so. It was, I know there's several papers, for example, within the Korean National Cancer Screening Program, which just to show the reduced mortality within the screen group. However, it wasn't done in a manner like in the randomized control trial. So we actually, so far, if I understand correctly, we don't have any direct clinical evidence yet to prove.
I haven't answered, but maybe I would give you the chance to answer first.
I can agree. I have read one of the last year, one article what was said, but I don't remember if there was correct control group. So I can look it up, but I can't say numbers right now.
It is true the data on this is very scarce, especially because we don't have many countries with established screening protocols, as you know, probably best of all here. I think it's very difficult to set up a randomized control trial on such a topic because of clearly ethical reasons. So it will be probably confined to comparing historical data to the actual outcome, what it is today, and then compare from different settings and different countries. The approach for gastric is very difficult because as opposed to colorectal, where we have at least two kind of lines with the colonoscopy and the fecal blood test, that are approaches that are established, that are working well, and that are kind of strategies that can be very, not easily probably, but straightforward implemented in different settings. For gastric, we don't have that.
And there's consensus, which is important.
And there is consensus. And for gastric, there's a lot of up and down because gastroscopy is, in many countries, too expensive. It's obviously invasive. A lot of patients wouldn't like that. There is no, pepsinogens are an option. There is no, but they're highly debated if they're reliable enough. I'm very excited to hear the sniff phone talk in a bit, how this is moving on. So for gastric, I think it's still all a bit wobbly, and I think therefore these data what you presented is very, very much needed, not only to understand what different tools we have, but also to get a bit of a perception what in different countries the idea is how these tools could be implemented and how useful they are. And again, this comes back now to heterogeneity. You showed the incidence figures. It's incidence, it's healthcare costs, it's different modalities. So there's still a very long road to go. And then is it effective or not? Ernst Kuipers presents usually very nice data where he compares different cancer screening programs, let's say PSA for prostate, mammography, and he usually makes quite clear that approaches taken for colorectal or for gastric are not far behind to what we already do for breast cancer. So I think it is another matter again of public awareness and kind of making this known, like with events of this week here, to push this forward. And thank you again for the data you presented there.
Could I just add, it's not only awareness, it's also about collaboration. So please don't ignore the possibility of working closely with patients, because at the end of the day, they're the ones that the media listen to, and they're also collaborating with clinicians. Together we will be able to make change, and together we have to make change, because this is a Cinderella cancer. We need to do something about it.
If I may, I have another question, and actually this is more a question not only to Geoffrey but also to the audience. And when you were showing the map of the activities of Europe-Colon, it was just the borderline with the EU countries. And I know that you do have office in the Moscow. We met the last summer people from there in your meeting, and actually here we do have people coming from Kazakhstan, from Kyrgyzstan, from certain territories of Russia. So are you interested also to have them on board, or maybe you do have, but you haven't just put on the map them? Or I would encourage also everybody to ask questions. You can ask also in Russian, and we would try to translate them. So just be free to discuss this.
We have translated the survey and the invitation leaflet into Russian. Because we have a group in Russia who is keen to work with us. As we saw, the incidence in Russia is very high. So yes, all we have to do is expand the list of countries, and we can include other countries, which, as long as we don't have to translate any more languages, we can work with what we've got and be very happy to.
Okay, any other research question?
Just for Evita, with what we've just discussed or mentioned, how do you think you will use your data that you just presented now? How would you think that will help to bring things forward, and how do you think you can distribute this to make it available to people to rethink gastric cancer screening?
We right now are preparing a paper about this, regarding this data we collected, and I think that very important part will be the information about the method, because as I mentioned, the upper X-rays, there are a lot of things to think about, because it's not invasive procedure, and we can learn what are the difficulties, and maybe teach professionals a little bit better into this method to look into it. Or we can talk with public organizations and government about endoscopy and how useful it is, and that maybe they could cover it for the patient if we can show that screening is needed in certain age group or in patients. And as well, we are working with volatile markers, and I think maybe for those doctors who haven't heard before about this method, maybe they looked it up, and we will try to point it out a little bit more in the paper too.
Okay, thank you very much. Do you have any further questions to the audience? Right, then I think we should move on. Thank you very much again for these two excellent talks.
Okay, and now we go straight ahead to the sniff-on issues, and I should just mention to be attentive, because actually Jan has been the reviewer of our previous paper in GUT, so I shouldn't have disclosed this, but he's a very important guy.
Okay, today I'm gonna tell you about, how does this go? Yes. So today I'm gonna tell you about the Sniff-On project, which is about disease detection through exhaled breath via smartphone. And just to go back and look at this in a more general way, the optimal diagnostic tool should be easy to operate, fast, low cost, reliable, safe and accurate. And 2,400 years ago, the Greek philosopher Hippocrates used to tell his medical students to smell their patient as an essential part of their diagnosis. And this is due to the fact that volatile organic compounds, VOCs, are created by the disease and then are diffused through the bloodstream and are emitted through breath, sweat, and urine. So thanks to their evolved sense of smell, dogs have been shown to be able to detect pregnancy-related complications and cancer, and that is due to the detection or to the sensitivity to these VOCs that are created by the disease. So this short clip may explain this a little better, and hopefully it'll go. No sound.
Organic compounds. When these molecules are released, they travel in the bloodstream. The molecules reach the lungs where they are emitted to the breath. The number of molecules is very small, just like one flower in a huge field.
So in order to try and look at VOC fingerprints, we have collected over 8,000 samples from 19 medical centers around the world, and what we did is we examined those by analytical means such as GCMS in order to try and identify a collective disease-related VOC fingerprint. Now, each sample was also run on our NANOS artificial ENOS array of sensors in order to also try and find sensor reactive fingerprint that would be related to a certain disease. So this is a heat map showing 17 different diseases and 13 different representative VOCs, and you can nicely see how the level of different VOCs nicely separate and create this heat map. And again, this may also be nicely visualized by this clip.
Right there when they leave the mouth with the exhaled breath is where the nano artificial nose can examine the discharged content and find those traces of cancer. When the molecules touch the sensor, the nano artificial nose identifies it and signals a warning. With the nano artificial nose, it will be possible to diagnose at the early stages of cancer and by doing so, save lives. As a variety of other diseases.
So again, the underlying principle under this ENOS concept is the fact that you have a diversified array of sensors all reacting with different affinities to different compounds, and the overall fingerprint or pattern of responsiveness gives you the separation between healthy and diseased. This is in a nutshell the principle of activity of gold nanoparticle sensors, and you have these nanoparticles covered or attached to functionalized organic molecules, different kind of molecules. Now these are nicely deposited upon the electrodes, and they are electrically bridging the electrodes. Now as the analyte, or in the presence of the analyte, the conductivity of this sponge-looking structure is changing, and we can read that as a change of resistance. This is just, again, in a nutshell, a representative different features of the responsiveness of different analytes towards a certain sensor, and this is the different sensitivity of different functionalized groups. The limit of detection here is about 10 ppb, which is pretty nice, and the sensitivity is, of course, the inclination of the slope of the curve here. So we're moving forward towards the nano array, the array of these artificial sensors that we have created. We took 59 different gold nanoparticle and carbon nanotube sensors, and have run our different 17 diseases or samples from 17 diseases and healthy controls to again create this heat map. From these, we chose 8 most indicative sensors that were reactive or informative towards gastric cancer, and have created our initial device, the VolgaCore device, which you will hear a lot from Jan later on. So this is the device, this is how it's operated. We call this the desktop device or the VolgaCore device. And these are the 8 sensors that were chosen to go into this array. This is how this machine looks like. It's not too big. And of course, this was done in collaboration with the University of Latvia, JLM, and others. These are some of the results emanating from a nanoarray similar to that one you've just seen the VolgaCore. And with after differential factor analysis, we were able to show that a discriminative model was generated that could separate gastric cancer from its pre-malignant stages after or under different setups. So, encouraged by these results, we actually envisioned the SNF-on concept. Now, this relies on 3 properties of the cell phone. First, the fact that it is continuously connected to the internet. It has a rechargeable source of energy, and it is a personalized device. So, quite frankly, if we can miniaturize the technology and have all of the sensor reactivity on the cell phone sent back to the server and do all the intricate calculations remotely on the server and send back a generated report, we can actually make these checkups really effortless and personalized, and hopefully making waves on the most important feature of cancer treatment, which is public penetration and early detection. So with that in mind, European consortium of 9 entities was generated, assembled, and launched. And I will try and tell you about some of our challenges and some of our results. So the main 2 challenges of the SNF-on project were really miniaturization and uniformity of response. In other words, when we make 10 sensors the same way at the same day, are they gonna respond the same way? This is an underlying capability if we wanna make a few prototypes, send them around the world, and have meaningful results that can be compared. So I will call this from now on the variability index, which is really the relative standard deviation of the reaction of the sensor to a certain analyte. So on the variability realm, we have actually moved from manual drop casting of these gold nanoparticle emulsions to a semi-automated nanoprinter, which can actually drop cast very, very precise and low amounts of this emulsion on a certain spot. On the miniaturization realm, we moved from TO5 12 millimeter sockets, in 12 millimeter in diameter sockets, to 8 sensors on one chip that are 1 millimeter in diameter each and are located on a chip that is 15 on 15 millimeters as a surface area. So really, we call this the heterogenic chip, where we can take 8 different chemistries, cast them on a single chip, and have this as the heart of our prototype. Now, in order to advance on our sensor-to-sensor variability, we have actually devised a multi-step optimization strategy where we actually revisited each and every property in the way we make these sensors, starting from general things such as the electrode sizes or spaces within the electrode, as well as the relative humidity at the time of casting and so on, and then going into different chemistry-specific synthesis properties and optimize them all. Later on, we have actually devised or came up with a MATLAB program which helps us to select these sensors that are most similar to each other and calibrate them so we can actually mount them on the prototypes to go into clinical trials. This is just an example of a certain chemistries. As I mentioned, we have 8 different chemistries that go into the heterogenic chip. And this would be an example of one of these. There are 8 sensors here, 8 identical sensors that are responding to escalating doses of octane. So each chemistry with its manufacturing variants were tested in order to find the lowest variability index of the different manufacturing variants. Now, with this chemistry, after selection of the best 70% and their calibration, we were able to reach 1.6% of response variability, which in my mind, or in our minds, was beyond our expectations. So each of these chemistries were optimized production-wise and were designated or located on one position of that heterogenic chip, the 8-sensor multi-chemistry chip. And the color code here is different curing time, different oven baking time. So we would cast those ones with the high oven time, bake them a little bit, then cast the rest of them, and so on. So this is again how the heterogenic sniff phone chip looks like, and this is how it looks like morphologically. And bear in mind that each of these electrodes harboring a different chemistry looks very different as expected. Yet when you compare the same position on different chips, they seem to be quite similar morphologically. So encouraged by that, we went ahead and asked ourselves, how do we select these different chips in order to find the best ones to go into the clinical trials? And I will make this as brief as I can, but quite frankly, the MATLAB program compares or finds the variability index of position 1 on each of these chips, and after exposure to 4 different analytes, it calculates the variability of this chemistry, then of that chemistry, and so on, to come up with the average variability across all chemistries. And then the program actually compares all permutations of choosing 2, 3, 4, etc. chips out of this set, with the selective criteria being minimizing the variability index of that chosen set after calibration. And so we have actually done that and chose the best 4 chips to go over to the clinical trials here in Latvia. And this is a chemistry-specific variability. You can see that not all chemistries behave the same, and some of the most variability is actually concentrated in one chemistry. But after choosing the best 3 out of these 4, calibrating them, and excluding this one chemistry, we were able to reach 3.3%, which was the best we could actually come up with, but also was beyond our expectations. This is actually how the sniff phone looks like. This is how the add-on device was first envisioned to connect to the cell phone. There has been many iterations talking about the actual design of it, and this is a more intricate close-up look. we have also added, in order to capture the sample for a long enough time, we have also added a microfluidic chip, and then 2 valves and a micropump. Now the application tells the user to blow into the inlet. After 2 seconds, these 2 valves actually open and the pump sucks in excuse me, the sample for 1.5 seconds. The valves then close and the sample lingers with the sensors for 60 seconds. The whole sensor response profile with some additional features that I don't want to get into right now are then sent to the server, and a generated gastric cancer risk report is then sent back and displayed on the cell phone screen. Of course, Yanni is going to tell you much more about this in terms of how this thing really operates and so on. So this is finally how the actual prototype looks like with the PCB, the electronics. We also have some humidity sensors that are stuck right by the inlet here, which are not depicted here. And this is how the cover looks like. We have collaborated with additional members such as Celix from Dublin, Nanovation from Israel, and of course the University of Latvia and others. With this, I would like to thank the funding agency, the Horizon 2020 of the European Union, and of course, thank you all. Thank you.
Let's go to Jan's presentation.
Let's see. Switch it off.
Yeah, I'm doing the presentation.
Okay. Yeah, I have some more here.
Oh, you have? Oh,
Yeah.
sorry.
No problem. But I'll keep it here, and I'll put it on the desk so you can use it later on too. Okay, so Gidi showed some of the work that was focusing on how we preparing the sensors, or how the Technion has been developing the sensor technology. I'm going to speak a little bit more about the instrument platforms that we have been building, not only within the SNIFON project, but also within the VolgaCore project. That was also a collaborative project together with the Technion and with the University of Latvia, which was finalized mid last year. This is a short outline, so I'm going to describe a little bit this VolgaCore project. I'm describing the VolgaCore breath analyzer platform, which is the desktop version. And then we have been deriving 2 different versions, the modular breath analyzer and the breath analyzer mini, which I'm just shortly introducing here, and then we'll move on to the SNIFON, see what changes we have done in order to miniaturize and also in order to change how the system is used, and we'll end up with some short conclusion and outlook. So I don't know how much I should say about the breath analysis itself, but the real idea behind it is that we're trying to capture the VOCs that are released from the exhaled breath. And there are a number of technologies that are used in that field, and it's a pretty young research field that has been attracting a lot of attention within the past, let's say, 5 years. There is, of course, established analytical instrumentation like gas chromatography, mass spectrometry, or GCMS combined technologies. There is also ion mobility spectrometry and proton transfer reaction combined with mass spectrometry. So there are a number of quite advanced instrumentations that are used that will allow you to really identify what kind of volatile organic compounds are in your exhaled breath. Now our concept is a little bit different. We're using sensor arrays based on rather small or simple sensors that are all not extremely specific, so they're all sensitive to a broader range of volatile organic compounds. So we need an array to really identify the pattern that is coming from the exhaled breath that is affected by the disease. So it's a little bit of a numbers game, which makes our task more complex actually than for the analytical instrumentation, where we really can pinpoint this is this volatile organic compound or that's this thing, and then you can identify the biomarker. In our case, we are in a statistics game. So we need data processing to derive to the end result, which is then the concentration of the VOCs or the identification of a pattern of sensor responses that would indicate a certain likeliness of a disease within the patient. But even if we're looking at the established technologies where people are looking for biomarkers, one of the real problems that breath analysis has is that there is such a huge variety of biomarkers or potential VOCs that could be interesting biomarkers in the field that it's really hard to pinpoint which are the specific ones. And it's not the case that there is one biomarker that you will have in one instance and that will define that this person's gastric cancer is typically a combination of different volatiles that are increased. So it is a bit of a numbers game. So getting enough data, getting enough studies to really validate that the method is working is the challenge that we all do have. And one way, of course, to ease that path to that data that we all need is to make the instrumentation more accessible, make the measurements more simple, and make the measurements more cost-effective and cheap and easy to use in the clinical environment. And that's the concept that we're following here with the sensor-based instruments. So the VolgaCore project is a Euro-Nanomed project with partners in Latvia and Lithuania, where we have been doing two things. We have been capturing breath samples into Tetlow bags and then transfer them into 10X sorbent tubes to identify really the biomarkers, to capture the breath and being able to send this breath sample. In this case, it was analyzed at the Technion, and we were looking for what are the specific biomarkers using GCMS technology in order to identify how to, what specific biomarkers we need to focus on. So offline GCMS was used to identify those biomarkers, and at the same time, as Gidi already showed, they have been using their broad range of sensors to see the response of the sensors to that captured breath samples. So that's the typical instrumentation, the GCMS instrumentation that you would need to run the samples. And one measurement takes half an hour, 1 hour. So it's a rather slow measurement. So the cost of such a device is maybe 200,000 euro, €500,000 in that range. It's fairly complicated to operate. You need a special trained person to operate it. So that is a major cost of the method. And our idea was or our concept is to replace this with an instrument that, first of all, does not need to transfer the sample to a central lab and does the analysis with a more simplified instrument. And the VolgaCore unit that you see on this picture, I have one here. So I should hold it myself. It's a little heavy, but I have one here, so you're free to come over and have a look at this, how this instrument is looking like. But you can see it's easily transportable. It's easy to install. It's also easy to clean and operate in a hospital setting. So the VolgaCore breath analysis is comprised of three main units. We have a sampling unit which allows you to capture the breath sample in the device. This is mainly a glass tube. I can open the device here and take the glass tube out. So that is where we're capturing the breath. You see this? Let's see. Where is the? How do I activate? So this is the sampling tube. So we have a disposable mouthpiece that plugs in here at the front that is thrown away after the patient, and we have a glass tube that's easy to sterilize after the patient. And then the breath of the patient is captured inside here. Then we have a temperature control unit which keeps the whole unit here at a controlled temperature of 40 degrees by standard. The reason for that is our breath is saturated with water vapor. If we're going below body temperature, then this water vapor starts to condense. And if water vapor condenses, it will capture a lot of the VOCs that we want to capture inside the system. So that is something that we try to avoid by having the whole system heated. And then we have a sensor chamber. In this case, we had 12 gold nanoparticle sensors that are individually exchangeable with signal conditioning unit and a pump to draw the sample from the sampling tube through the sensor chamber to the outside. So that's the sampling method. We have this glass tube here that is exhaled into. We have a buffered breath volume of around 30 milliliter inside that glass tube. We have a sampling point. You can see the glass sampling point here. So what the patient does is he exhales into the mouthpiece, into this glass tube. We are measuring the flow, the exhalation flow, and then when we are identifying that the exhalation has stopped, we're taking the alveolar part of the breath, so that part of the breath, that's the end-tidal part that's coming from the inside of the lungs, not from the mouth, and transferring that using the pump to the sensor chamber. We also have a number of additional sensors here. We have temperature and humidity sensors, and we can also add CO2 concentration measurements inside the system for additional parameters. So that system does allow us to capture the relevant parts of the exhaled breath. We could even decide, since we know when the exhalation is starting, we are monitoring the breath, to capture the part that comes from the upper part of the respiratory system or from the mouth. If we are interested into diseases that manifest themselves into the mouth part, then we could take the exhaled breath from that part. But typically, for all the diseases, for gastric diseases, we are interested into the part that comes really from the lungs. So I've already mentioned that we have temperature control, so all the fluidic parts inside the system are kept at a constant temperature above body temperature. That's how the sensor chamber looks like. There's a little bit of technical things around it that's probably a little boring to explain in detail, but it allows us to precisely measure all the sensor signals of 12 GNP sensors inside. This is how the system looks inside. Here is the exchangeable mouthpiece. That's the glass tube that I'm holding inside here. We have this lid that can be opened easily, so we can exchange the glass piece easily, sterilize it, put it back in, and be ready for the next patient to measure. This is the compartment for the sensors, and pumps and electronics are also sitting below here. What we've done then, in the next step, we've improved the system. Throughout our collaboration in the SNIFOund project, we had quite significant improvements on the sensor technology. We've gone away from these individual sensors to a sensor chip that holds 8 sensors on one chip. So we needed to change the electronics inside, and that also gave us the opportunity to build a modular system where we could include different sensor technologies. So now we have a new assembly inside, which has the gold nanoparticle chip here with the dedicated electronics behind it, and then 2 other sensing technologies based on semiconducting gas sensors that are commercially available. So we now have a system that allows us to test more sensors in a setup. That's the gold nanoparticle chip. You can recognize the SNIFOund chip in here. You can see here how that SNIFOund chip is held onto the chamber. The gas flow here, the gas is transported here from the beginning, exposed to the gas chamber, and is exiting here at the hole to enter the next sensor chamber. That's the metal oxide sensor chamber with 8 metal oxide sensors, a very small internal sample volume. And then we have a very new development that is now just hitting the market in this year, which are the digital metal oxide sensors. Those were actually, those are now brought into the market with a target of being embedded into mobile phones. So for us, this platform allows us to test drive new sensor technologies and their applicability to breath measurements, but also with a focus on those existing technologies that are now already being implemented into mobile phones. So those kind of sensors, you can already find mobile phones that include those sensors. So the idea really is to see what is technically available, what can we learn from technical developments, and how can we convert that into something that helps us to understand medical needs. That's another development that we have been doing, miniaturizing the system furthermore. This device is still quite expensive to make, so we were looking for possibilities to extend the reach of the system, and we've made a small size version. Since we have the miniaturization onto one chip, we could reduce the internal volume, we could reduce the cost of the whole thing. So that's a new version that we have been developing, which we have available now, and we've been doing already some first tests with that system. And again, here we can implement the GNP sensors and combine it with a few number of extra sensors. We have also developed a user interface for clinical use, which is actually fairly easy to operate. The main thing that needs to be entered here is a patient ID. So we're not taking the patient name or things like that. We're just taking the patient ID. We have a field that we have to have in there for ethical reasons, that we need the consent from the patient. That means that the nurse or the practitioner needs to check that the patient that is being investigated is okay to be included into our data analysis. And then we can enter here a field for different anamnesis. Typically that's left empty because most of the time that kind of information is already available in the clinical systems of the institution, and then we only need the ID here. And then the real user interface is quite easy. There, the nurse only has to push one button and the rest of it is automatic. The system goes through a number of steps. We also have some LEDs on the system that give some optical feedback to both the nurse and the patient. And we have an easy to understand message up here that can be also translated into different languages easily. So this kind of system is already in use in some hospitals, and it's fairly easy to operate. They just click the button, the system goes through a step, the whole measurement takes around 5 minutes typically until it's finished. So the patient sits down in front of the instrument, the nurse goes through a short checklist to make sure that the patient is in the right state, starts the measurement, and then there is a display which shows to the nurse that the exhalation process has been done properly, and all the data is then gathered and stored in a file automatically, and once the measurement has been done, the information is stored and the system can be ready for the next patient. So to give you some idea on the size of those, this is this modular breath analyzer system, or the Volgacore unit. They are on the outside, they're identical. This is the new low-cost version of it, and this here down here, that's the sniffphone chip that you have seen before. I can also open this here to show you that actually the electronics is only half of it. In this case, the pump itself is missing, which would be sitting here. So as a demonstration object, you can come here and take it into your own hands to see how the system would be looking like. So the sniffphone itself is the idea to even drive the cost down, to make something that could be used on a personal level, not at a practitioner. It could be something that a user could be buying and using at home. So without needing to go to the doctor, he could perform the breath measurement at home. So that's the full electronics inside. The idea is really low cost, small size, easy of use, a personal device, and we've chosen the mobile phone as a platform because that's something that's now pretty ubiquitous. We have the communication built into the device. We have power supply into the device. So at the moment, this is connected with a short cable to the mobile phone. So you can enter all the data or operate the device with the mobile phone and then use this device to do the exhalation process. Why did we choose the smartphone? Well, there are a number of things that make the smartphone a really interesting platform for medical purposes. Not only it's cheap and available and connected, but it has some additional information. It has GPS data, location data. It has time data. You can have additional movement information. With the new mobile phones, if you have a watch or an iPhone or something, it captures your motion per day. So it can also tell us something about the personal status. Have we been exercising? Have we been sitting before that? So all that kind of information is interesting really to identify in what kind of condition is the person at the moment when he's doing the measurement. So it's a rich platform that we can tap into and that we can use for that if we're really focusing on the personal data. Now for screening purpose, that might not be the most suitable platform, but for monitoring purposes or treatment purposes, that might be a good thing. I mean, you could use your breath to indicate when is the time to get more medication, or am I improving, or am I getting worse? So that is, I think, where this kind of a platform has more use cases. That's something that Gidi already mentioned, that we're not actually doing the data analysis inside the phone. We're storing the data. We're getting the data from the phone, transmitted to a central server, and doing the analysis there. One of the reasons is that, of course, we need to be very critical in what kind of information we're giving to the patient. Now, let's say you're really using this for gastric cancer. Do you want to have a device at home, you're exhaling into it, and it tells you after, congratulations, you have gastric cancer, you have 6 months to live? I would rather have a professional person dealing with that kind of information, giving it to me bit by bit and with some more validation. So that is, that I think is one part that we should not give out of the hands of the medical practitioner. So it is a tool that is to be used in a collaboration between the patient and the medical professionals. This is a simplified mobile user interface that we have been coming up with. Maybe Mina is going to comment on this also a little bit. So we've been doing some tests, some usability testing. How would it be? We need to transform it into something that's easy to use. So Mina will be focusing on that part. And I think I should conclude now. Breath analysis is a very interesting field from a usability point of view. Nothing is more easy than to give your breath. It's non-invasive, it's a short process, everybody can do it. I mean, so that is the nice part. Making that work is really tricky. So there are a lot of challenges that we need to do, and one of the big challenges is getting enough data. So our concept here is to have some platforms, to build some platforms that allow us to gather this data so that once we have it, once we go through it at one time, we can really find a solution to that problem. And there are many, many applications, not only gastric cancer, also other diseases where such kind of technology would be very interesting. So I think I should hand over to Mina so she can conclude the talks from the SNIFON project. I'm leaving this here.
Yes, that's great. So I will start. So hello everybody, my name is Minna Kulju and I come from Technical Research Center of Finland, from the PTT shortly. And let's see if I can use this. Oh, yeah. So what we are doing in the SNIFON project is that we are gathering user requirements about the SNIFON setup. And as Jan already presented the setup, I can, Should I? Yes, you can click the video. So we have our mobile phone, and it's attached with this sensor. And then first you log in, you give your password and username, and then there is the instructions how this is used. So you go through them quickly, the instructions, and then you click the new sample. You can see your own data, and you can edit the data if there are some changes. And then it reminds you that you have to be not to smoke, you have to do it indoors, and of course you have been fasting overnight. Then first it takes the surrounding air measurement, the baseline measurement, that when that's taken, okay, now it's instructing how to take the breath shuffling. It records, and then luckily nothing very serious in this case. So very easy. And this was the setup we were studying with the users. But before this setup, we went, we interviewed gastroenterologists in Germany mainly, also some couple of Russians were interviewed, how they see this kind of breath sampling as a screening. And then we made, with layman's, the open web lab study. It's the VTT's web tool to gather users' feedback. We put there some user stories, kind of scenarios, and evaluated them with the users. And when we had this setup, we went to the shopping mall in Tampere in Finland, and we had experiences of 20 people tried this setup and give their feedback. And those plus 10 people, they were the people that were too old to handle the mobile device or this kind of device. So then we just introduced the setup, and then we were interviewing them and asking their opinions about that. And in VTT, we went, we showed this setup for 9 participants, 9 usability experts, and then we gather more precise usability results from them. And in Siemens Healthcare in Germany, 12 participants, which were more technical experts, went through this setup and give their experience of that. Okay, so what did gastroenterologists said in their feedback was that, okay, sensitivity and specificity is very important if you are using this kind of breath gas test for screening. Preferable, both should be over 90%. Some of them comment that, okay, the false positives are not so how do you say, so critical, because in following tests you will notice that, okay, this was false positive. But the critical is the false negatives, because if you don't notice that the patient have the disease, you may get troubles, of course, when you are dealing with the cancer. And of course, they commented that this is also the political decision in the medical economy, because where they set the cut-off of the sensitivity. So if you get more false positives, then it's more cost. Also, the test should be low cost, at least cheaper than the follow-up tests. And there was said that maybe some 10 or 15 euros is good amount. And of course, it has to be non-invasive and easy to perform by the user and as well by the clinicians. And of course, the patient acceptance is very, very, very important. So, as it has said that those endoscopies and they are not so, how do you say, accepted by the people. So maybe this kind of easy to do and non-invasive is more accepted. And there was commented that when you are screening the breast cancer, there is this radiation which is not very safe for the patients. So breast sampling is maybe better also for that reason. When they were asked what is the way to do the screening or diagnosing the gastric cancer, now it's the endoscopy. But before the endoscopy, the gastroenterologist said that they would like to have some kind of reliable pretest. So this breath analysis could be one. And it has also to detect this early stage of and also this precursors. I'm sorry, the English is very hard. It will be also important that if you have this kind of breath analysis. The gastroenterologists were asked whether they see that this gastric cancer screening is important. And they commented that in Western Europe, the incidence rate is so low that there is maybe not need for the screening, but it's different in the Asian countries, for example. And if the breath analysis could be expanded to the other diseases, like lung cancer, colon cancer, breast cancer, it would be more use for this kind of method. The critical aspect of the SNP phone was commented to be that the data security, the surveillance of the patients, and of course the false positives and false negatives. And if people can use this kind of setup by themselves in the home, the self-testing has some ethical considerations. And the positive experience and aspects of the SNP phone, if it's tested that it's too sensitive and specific enough, it would be very useful. And if it's provided that it's working correctly and it's reproducible and reliable, then it's seen as a very good method for screening. About the ethical issues, the gastroenterologists raised the issue that how the results will be communicated to the people, and of the people's surveillance. So if the people are doing the test daily basis, for example, so it may I lost the words every time I'm going to present something. So if people are doing it daily, so they are harming the test, because they say that every time you have some kind of screening test, in some cases you get some false results. So this has to be very strictly processes how people will use it at home. So about the layman thoughts about the sniff phone concept. So in general, people were very much like this kind of idea that they could have the device at their home so that they can test themselves, and especially in the very early phases. And there were some people in our evaluations whose relatives have had some kind of gastric cancer, colon cancer, or that kind of times. So they were more eager to have this kind of device by themselves. When we asked them, will they trust this kind of device? So they say that of course there have to be studies that this is reliable, but also it was interesting when we asked that if, for example, you give this kind of device from occupational health care, or if you buy it by yourself. So they said that, okay, if it's some kind of healthcare center that gives you the device, it's more reliable than the one that you can go and buy yourself from the pharmacy or some other store. Also, the laymen were willing to have this kind of device so that it could detect also other diseases than only to cancer. And they were mentioning the blood sugar measurements and other metabolic diseases. When we asked whether you would like to use this device independently at home, or do you want to go, for example, in Finland there is kind of health kiosks where you can, for example, measure your blood pressure, and there is some healthcare professional helping you. So especially older people were willing to use it in this kind of setting, that there is always help available. They were not so trustful that they can use it by themselves at home. And of course there was worries that, okay, who will be responsible of updating the device and maintaining the device if you use it independently at home. Okay, then about this, how this concept works, some comments of that. Okay, the guidance is very important. If you use it independently, the people tend to rely very strictly on the guidance and instructions that they are given. So it should be in line with the design. And we had some images, but also they were willing to have some kind of audio feedback or video, for example, that how you take the device to your hand and how you blow. About the breath sampling, now we have this device. So we were thinking of how this design could promote people to handle this device in the correct position in the hand. And in this device we have some holes in the back. So people were a little bit suspicious that which hole I should breathe. So maybe marking the hole with some other color or something like that would promote them. And what we noticed was that people tend to press so that they can still see the device, but the distance should be like 1 or 2 centimeters. So maybe it's not so natural for people to take some awkward device so close to your face. And about the results, as Jan already told you, the the given the results should be carefully designed, so you don't give them too much worries that, okay, now there is two options. The one was what you see in the video was that, okay, everything is okay, no signs of gastric cancer or some other diseases. And the other one was that, okay, there might be something, but we will suggest that you contact your healthcare professional to get more reliable results. Of course, people have to be told that that this is only the pretest, that the results is just directive, that you get more reliable, and the diagnosis, there is the need to have more thorough clinical tests. But most of the people thought that, of course, they would like to have some results when they have given their breath sample. So we asked that whether is it just enough that you give the breath sample and then that's it? But most of the people say that, of course, I would like to know if there is something. Okay, what we are going to do next is the sensor development is going on. The sensor device in the future, it could be like this one. You can attach it straight to your mobile phone. So we will evaluate that with the users. And of course, the mobile user interface is going to be developed accordingly to the feedback we have. And also we have some first demonstration of the professional user interface. So when the professional gets the breath samples, so how the professional can look the samples and what kind of indicators there is about the diseases. So, yeah, that was pretty much all I have.
Thank you very much, all three of you, for a very good overview about a great project. If I could ask you to also to come back forward, and then we wait for questions from the audience, if there are any. Let me start with the boring facts. So what are the costs of the device, and what are the per test costs at the moment, or what are you estimating to get on in the end?
We just had a discussion about that.
Yeah, I mean, the problem is at the moment we are on the research level, so we're building instruments, 5 instruments, 10 instruments, and of course that cost that we have there is not comparable to the cost if we build, 5,000 units or 20,000 or 50,000 units, if it is a personal device. So the cost on the technology really scales with the amount of instruments that we're building. We are at the moment estimating that for the desktop units, the production cost that you would be having at the moment is something in between 3,000, 5,000 euro. But then of course you need to add distribution costs, services and stuff around it. So that also depends on how, how this is brought to the market, where the cost is beared, how the cost structure is working later on. If you're talking about the mobile devices, there is again a variability in there depending if we are integrating it within a mobile phone. As I mentioned, there are already some gas sensors that are implemented in the mobile phones, and I can tell you that for the gas sensor companies to bring a sensor into a mobile phone, the acceptable cost for that gas sensor is below $2. So that's the extra cost that the mobile phone companies would accept for integrating a gas sensor into their mobile phone. But of course, we're talking about multiple millions of sensors in that case. If it is something, like like this device, a small add-on device that we have already been building with some existing gas sensors. That is something that could be in the range of 20 euro, 50 euro, something in that range. If we're talking about a more complex device that we have here with the sniff phone project, if we produce something like this in numbers, the cost could be in the range of $100, $150. But again, then you need to think about if you market it, if you distribute it, how do you do that, and the cost associated with that. So I'm talking about production costs.
And the per test cost would be depending on what you're going to analyze, or is it kind of in a certain range that you kind of could guess
that
already?
Depends if you really have consumables. The nice thing about the gas sensors is that they don't have consumables. Essentially, a good gas sensor could live for 10 years. So you could make, 1,000 tests with one sensor, and it would be still good to go. So it really depends, how long can you use an instrument, what kind of so the instrumental cost, if you look at this, is going to be negligible.
Yeah.
There might be some cost for cleaning equipment, or you would have the cost of if you need a medical practitioner working with a person, then of course you have that cost, but it's more the labor cost that you have around it. If it's done at home, then for a repeated test, you purchase the instrument and then you can use it for multiple times.
Actually, when we were debating, we were thinking of production costs for sniff phone running between $50 to $100, and we were wondering what would public acceptance be like. And I'm wondering how many of you would be willing to pay, say, $200 for something like this that you would be able to check at your own leisure whenever you want, in private. How many would pay $200? Anyone? No? 100? Yeah, 2, 3, 70, 50? Yeah, 50.
Yes.
No, I'm talking in a utopic world that you get this and you know it's accurate. You can actually check yourself whenever you want, repeated times before.
Check for what?
For gastric cancer.
So, but I understand it just gives you a green light, or it says see your doctor.
Yes.
Is that correct? So, but if it tells me see my doctor and I look for gastric cancer, then I kind of already know.
Yes, but you see, this whole thing is because we realize for whatever reason people are reluctant to go to the doctor. I mean, it's a hassle, it's time, it's exposure, it's parking. I don't know. It's the whole thing,
I mean, we've been discussing here screening things, and I think for a device that's used for screening, this could be a pre-screening method. So you have a breath test that shows, okay, there is an indication that a real screening might be advisable. So in that case, we're reducing costs because we can reduce the amount of patients that go through a full screening.
Okay, but if I may change the question you were raising about the cost for screening for gastric cancer, if we change the indication and say that this device can detect in a timely manner your flu, would you be willing really to check on everyday basis to, at this time of the flu epidemic, that you have to take the medication? So, no.
Because you already get it, and then,
that is not the point, because if you are starting to take the medication earlier, you are protected. If you are too late and are waiting for this, you are not anymore.
Yeah, I mean, for me as a lay person, as not a medical person, it's sometimes hard to really identify, do I have a flu, or is this just a cold that will go away without doing anything?
A man flu.
And more importantly, I think if you have kids and they have something and you want to find out, do I need to treat this kid? Do I need to take the kid to the doctor or somebody else in your family? I think those are scenarios where a device that could help you to make that decision would be something that I would actually pay money for.
And in the first phases, we were asking whether this is device for the screening or is this device for the following up it. So if you have had already something that could be in the future to be a cancer. So I think at least the laymen's were commenting that okay, the screening is a little bit scary, but following up is something that, yeah, I broke it, sorry. So, too nervous. I'm sorry. Well, so that the follow-up is definitely something that they would like to have.
Can I? Yeah. Let's. While the microphone.
My concern is that you're setting it up for the worried well, and not for the general population. And I think that's one of the main considerations you have to think about, taking it out into the population, because we know even in screening schemes that are available, it's the worried well who complete them. It's not the people who really need to complete them that actually do the studies. So that's my concern from a patient perspective.
And I think, well, I would be also concerned about the people who resort to alternative therapies or self-treatment rather than going to see it with really unconventional treatments, and that can be very dangerous, instead of actually trying to go and consult with a medical practitioner.
Yeah, I was also wondering, like, I don't know actually where the technology is currently standing, but let's say, like, even if it's like very well validated, etc., but still, what if it gives a false assurance basically to the people, like, on a daily basis, and then
so that message is also tempered. So we can say up to now we don't see anything out of the ordinary, but bear in mind, and what I'm saying right now is not validated, but at least conceptually we can actually raise the accuracy dramatically by multiple checkups. So you check now, you check maybe later on in 1 or 2 days. If they're all clean, then chances are you don't have symptoms. But it's always, I mean, we're always running the risk of having,
I was really fascinated, and I think it's really interesting. The thing is, because can those small devices really replace with this GCMS? Or
No,
so
they don't. The difference is that the GCMS gives you a different type of information.
Yeah.
It will analyze the breath and give you exactly what kind of VOCs are in the breath at what concentration. So you get the full information about the whole breath. These devices will not do that. They give you a sensor response pattern that we need to compare to our database of sensor responses so that's why I mentioned at the beginning, this is a numbers game, that we need to establish this kind of influence on the sensor pattern of the diseases that you have. It's a more indirect method. That's also why we think this is more appropriate as a pre-screening tool. So we need to validate the results with a more intense, maybe
has it been like validated, or
that is the process. I mean, we have doing a lot of clinical studies, but of course all those clinical studies are limited in number of patients. So it's a little bit a hen and the egg problem. You need to build an instrument that you can build out and give out, and we are in that process. So it's not been fully validated. That's the honest answer. But to get there, we need to build the technology first. So that's the step that we're taking now.
And how do you measure reproducibility? Do you have any published data on that? Like, if a patient or a person does it at one point in time, then later, a week later, 1 year later, just to see if the measurements are reproducible.
That's all part of the validation process, and on the technical development also, because we are trying to. So there's two things happening. We have the data from the GCMS measurement would give us indications on what kind of volatile compounds should we focus our sensors on. So we're trying to trim those sensors to capture those volatiles. But then, so it's a technical development process, and also a process that you have seen that we're spending a lot of resources into to make sensors that really capture those things well. And then there are two things. You look at sensor reproducibility and sensor stability. You can do that without patients. You can do this with using, test gases, test parameters to make sure that your sensor signals are stable. But then you need to compare that in the real life, because the real life is also influenced by other things. There might be poisoning effects, there might be different environmental conditions that we need to take on. So that all plays into the role of repeatability. So that's why our real problem is we need to generate more data. We need to build more of those instrumentations to really validate that method.
But maybe to add on to this a little bit, tapping onto your question. So as Jan mentioned, there are two kinds of reproducibility: the reproducibility of the sensors in the lab and the reproducibility of the device by people giving it their samples. And so reproducibility in the lab I kind of touched upon, and to let you know about the drift, we have like 6% drift in 3 months. And other things that we could actually try. And of course, you ask yourself, which are the relevant Vox to try? You try 4, you try 5, you try 20, but then, that's limited. But then again, for the device itself through clinical trials, there's some nice results that have just been coming from the clinical trials done here in Latvia. And INISU was giving us some of her statistical analysis. And apparently, I was surprised to see that indeed there is, as you just mentioned, a sample given today and a sample given by the same person a week later, take 20 people, and would it recognize that? Would the samples that were given by the same people be the closest 20 times? And apparently, she seems to have shown it is the case. So we'll still have to make sure indeed that, that's not by chance, but, it's always, I think it was 120 people last size of the clinical trials. Yeah, even larger. So let's see what we get from this and how the statistic looks like. We're probably over 90%. Lab results show 96%. So,
yeah, it's a continuous development, I would say. We see that we have some good results there, but validating it, and then we have to take it from one place to the next place under different climatic conditions, with more variability. If you look at a personal device that people have at home, then you have much less control about the status of the persons, what they have been eating. You can't tell the person to fast for 12 hours before you do the exhalation, because that's a little impractical for a personal device. So
it's dietetic,
the more the
dietetic, because you don't eat for 12 hours. That's a joke.
So what I hope will happen with that technology is it will start, on a more restricted basis and then spread out. And the more data we have, and the more we are optimizing the system, the more we can extend the use case, and the more we can cover with the technology. But we need to start somewhere.
Just one quick one, thinking of your nice heat map that you showed in the beginning. When you have a patient with gastric cancer and Crohn's, will that kind of, just as an example, when you have 2 or 3 diseases in the same patient, will that really mess up your results? Would you be able to pick up all 3? What do you estimate for these ones?
Oh, you're saying
if someone does the test and he has actually 3 of the conditions you show there, or let's say 2,
yeah.
Because you said, okay, this is now the test for gastric cancer detection, but maybe there is some kind of influence.
So this gets complicated, because you could have someone who knows he's got gastric cancer and doesn't know he's got Crohn's, or vice versa. And so these data could be contaminated, right? So what we have is the naive collection of the data, knowing what they are, and separating them, and having the sensor respond and making a heat map out of that. But you're getting at a complicated story here.
Sorry.
No, that's perfectly great.
Yeah, what would typically happen from a statistical point of view, that you will get a new pattern that is not identified by the others. So you will get an information, probably, there is a risk for that, but it's not really conclusive. So And then it depends how you set sensitivity. If that is a patient that you say, okay, that should go further investigation.
Picking again the pre-test scenario, then you have something that's flagged that's like something is kind of dodgy, you should see your doctor.
Just remember these are averages, right? So it's not, so you could have one that's a little bit of an off shooter, and that may be because he's got Crohn's or other things, who knows.
Thank you very much. I think also that's fascinating, and I can't wait to see that in practice in the end. Any further questions? Otherwise, thank you again, and we will proceed to our host Tomasis, who will tell us about the public perspective of the broad use of antibiotics.
Okay, we are actually a bit behind the time, but I cannot really promise that I'm going to spare more time, but I will try to do the best. Actually, we are changing the topic. We are changing from technical issues to completely different issues, to microbiome, to the testing of microbiome and the potential role of microbiome. And let's see where we are. And actually, I have even twice more difficult issue, because when speaking on these topics, I have to get into the shoes from the gastroenterologist to the shoes of public health specialist, and then I have to get back and come to the point to the gastroenterologist. So these indeed are the topics what I'm going to cover: the gastroenterologist viewpoint on the issue, public health specialist viewpoint, and then to discuss briefly the resistance issues predominantly on microlides, duration of the treatment and how does it impact on the result. In the case if we go for mass eradication, what would it mean to antibiotic consumption? Briefly, not in detail, on cost effectiveness, and I will propose really as a hypothetical scenario, and this is much more a provocative scenario. I'm going to conclude my talk. So what the gastroenterologists are saying, and gastroenterologists have common opinion, and this common opinion has been summarized first of all by Kyoto Global Consensus a couple of years ago, saying that it is appropriate really to search for Helicobacter in everybody, in healthy individuals, in particular in the countries of high risk, but no difference which countries to search in everybody, before the precancerous lesions have developed, and all the HP infected individuals should be offered eradication therapy unless there are competing consideration. Maastricht is still adding a bit more to this. Of course, we know that HP eradication would prevent gastric cancer, and it is estimated to be cost effective, at least in high risk areas, that there would be economic benefits also in other risk areas, and this screen and treat strategy is recommended in communities with high risk of gastric cancer. So if you are taking Baltic countries or Russia or Belarus, or not speaking about Kazakhstan or Kyrgyzstan, everybody should be searched for Helicobacter and everybody should be treated. What would it mean? It would end up, for instance, what we've heard in Yakutia, in treating 100% of all the population with antibiotics. So would this be beneficial, or still there would be some risks related to this? And even in countries like UK, in other communities with lower risk, this should be considered. So these are the recommendations, the international recommendations, the very latest recommendations. What do we have? On the other hand, no country globally has really implemented this strategy. Okay, it is Taiwan that is trying to do something, but not really on a country-wide basis in some of the communities. Probably the country that has made the biggest step towards this is Slovenian Gastroenterology Association, because our friend Bojan Tepes has clearly recommended in his recommendations that have been published that the society is recommending recommending nationwide HP screening and treatment to everybody that is HP infected. So that is our official position, although it is not really accepted so far by the government. But do you think we can support Slovenia? So we have good reasons really not to do this, because of Slovenia, Latvia didn't get into the final quarter in the recent championship. So definitely we cannot indeed take it in immediately. What is the situation really in the countries with the highest burden? And these are the data from our friend Dmitry Bordin and his group. They have been investigating and actually also questioning physicians. And only, of course, a big proportion of the physicians were positive. That is what we would also expect as a general population. But close to 50% of those that knew that they are HP positive didn't accept really the eradication treatment. So what we can recommend to the general population, in the case if physicians are really not accepting this themselves, the majority are, but definitely not all. But we could look also, and now I'm stepping into the public health shoes, because really the public health specialists have not been participating in developing these guidelines, and we have really seriously to consider this. And actually a presentation like this I was giving during the UEG. We tried very hard to get a public health specialist speaking on this. We didn't succeed to find one, so I had to take this presentation. But actually what they are saying, and thanks to our antibiotic use specialist, Professor Uga Dumpis, this is a slide what he recommended. What is really the concerns of the WHO by 2050? So the major cause of mortality will be antimicrobial resistance. It will be a higher burden than all the cancer diseases in total. So, and now we are speaking just treating, so preventing gastric cancer. That is a very minor part of this, and potentially increasing this part of the pie. So there might be really problems to address this. And this is definitely what the public health specialists are considering. And now we are coming only to Helicobacter, but Helicobacter is really the minor player there. Helicobacter is important. That is a major cause of cancer. We know that we are decreasing the burden of cancer by eradicating Helicobacter. But so the success of eradicating Helicobacter, and we know very well, and these are the Maastricht guidelines, that you should use clarithromycin-based treatments only in the case if the resistance is below 15%. And what is the situation? In most part of the Europe, actually in southern part of the Europe in particular, the resistance is higher. We are lucky actually in Latvia and our neighbors as well, having really resistance figures to this. But prior really to choosing the appropriate treatment for eradication, you should know the eradication, the resistance rates of to clarithromycin, and is this the real practice? And this is a map from the European Helicobacter Management Registry. So all the countries, or most of the countries, are using triple therapy, although most of the countries do have the resistance patterns that it shouldn't be used. So there's once more some controversy in this. David Graham, the globally god of Helicobacter, and his historic consideration that good Helicobacter is only dead Helicobacter, so treat and everybody. He's considering that any eradication treatment that is being used should achieve at least 90% effectiveness. If the effectiveness of eradication treatment is lower than that, it means that it's inappropriate treatment and you should go for another one. So, but the big question there, and David hasn't answered this, does this apply also to population-based prevention strategies? Or this is treatment? Because this is definitely treatment and this is related to the patients. Okay, what is the efficacy of those treatments, and once more data from the registry, we are at the 90%. No country is reaching 90%. So in none of the countries really this is accepted. And what our friend from Spain, Professor Gisbert, has divided really high and low clarithromycin resistance countries. You can easily see that those where the clarithromycin resistance is high definitely are performing much worse. But 50%, 60%, 55%, these are really unacceptable rates. So really the success is far below that should be really the target. But I'm coming now back to the issues of the long-term impact of antibiotic use to microbiota. Definitely the antibiotic treatment, let it be eradication treatment or any other, is destroying the ecosystem and destroying the not only Helicobacter and gastric microbiota but also other gut microbiota. After ending treatment, definitely we expect that the previous microbiome, except the Helicobacter, is really coming back to the previous state. But is this the real situation? And actually that is not always the case. And we do have currently few studies demonstrating this, that after eradication treatment there is some still perturbation in the gut microbiome, also after a prolonged period, even up to 1 year or 18 months. So part of the patients definitely is coming back to the previous state, minor part, but still a significant part is still not coming back, and they might have the problem. And even more important are the resistance issues. That also has to be proven that either clarithromycin or metronidazole can really induce the resistance, either in enterococci or enterobacteria. So they could really be responsible for living into the gut only resistance microbes, or not definitely only the resistant microbes, but a proportion of resistant microbes, not the ones that were there before. And actually there are few studies from mainly Lars Engstrand's group and others showing that this perturbation or the persistence of resistant stains could be up to not only 1 year but even up to 4 years, 1 to 3 years following the standard clarithromycin triple therapy. So definitely there could be adverse events, not only the beneficial events. And I would like to point your attention to this 10-year-old study that has been looking at the pharyngeal microbiome. They haven't been using the molecular biology methods, they have been using the routine methods, and it has been the treatment of only, if I'm not afraid, 7 days. Dose of clarithromycin the same as for eradication, and what we recommend now is twice as long as this therapy. They have been following the individuals for 180 days, and we're testing the throat microbiota. And what they found that really the macrolides have the most important, were resulting in significant increase in the macrolide resistant streptococci. And actually this hasn't been considered too much when we are speaking about a mass eradication of Helicobacter. So about the duration of the treatment. What we had in Maastricht 3, and these are each of them are 5 years apart. Maastricht 3, 7-day treatment was recommended. 5 years later, it was said that okay, probably you should use 10 to 14 days. That it is increasing the success rate by 5%. It was not exactly told that you should use 10 to 14 days. Now, the recent Maastricht guidelines, we are saying that it should be 14 days unless other treatments have been proven to be effective enough. And the other consensus, the Toronto consensus in Canada, they are also without any question mark. The same in the United States, they are saying the standard is 14 days. On the other hand, more you are using antibiotics, more you do have the antibiotic pool, more you do get the resistant strains, and this in the gut in general, not only speaking about the Helicobacter. And that has been proven in a quite recent study by comparing the antibiotic consumption and the gut microbiome in these countries. So, of course, it is inappropriate to use a small dose. It is inappropriate to use too big dose, but you should avoid these medium range that is selecting the mutant strains. But actually, these studies have proven that every day you are longer using antibiotics, it's increasing more the number of resistant strains. So on one hand, we are extending the treatment to have more effective, higher effect of the eradication treatment. On the other hand, with each day we are extending the treatment, we are getting more resistant strains. So how to deal with this, and actually how it will reflect to the antibiotic use in the country, and what is usually used argument by gastroenterologists that, okay, if you are using once per lifetime 10-day or 14-day treatment, maybe even 7-day treatment, this is really nothing if to compare to the regular antibiotic consumption the population is subjected to. But is this really the case? And actually, I have been calculating this together, and Professor Dumpis was helping me a bit with this, calculating what would happen in Latvia in the case if we would recommend eradication to everybody or to particular groups. And we are quite lucky currently in Latvia that Latvia is quite low in antibiotic consumption, although definitely we cannot say that everybody is treated appropriately, but nevertheless. And what is going to happen in the case if we are going to eradicate everybody? So those are the figures from our official sources of the clarithromycin and amoxicillin consumption, and the dotted line would be the trend in the case if we are continuing the previous strategy, really not going for any mass antibiotic consumption strategies. So in the case, and I have got three different scenarios. One scenario is just eradicating 1 year of age. For instance, when the people are getting adults between the age of 17 and 18, or it could be different between 20 and 21, it doesn't matter, the numbers are approximately the same. So we eradicate only those, and there could be a good rationale to do this in this age group, definitely. In the case if we do only this, we are increasing both clary and amoxi consumption twice. Is it this little or is it much? I assume it is still quite much if we are doubling the use of antibiotics in the country. In average, in the total country, I mean. If we are going to eradicate maybe 40 to 64-year-old cases, those that are within the G-star group, and we don't eradicate everybody at one single year. We have this as a 3-year campaign, eradicate 1/3 every 3rd year and have 70% compliance. In this case, we are going maybe from these 2 daily doses to 8 daily doses. So, meaning that we are increasing 4 times. And if we want to eradicate everybody with the same intention, in this case we go here much upwards. 6 times we are increasing. So this is indeed not a small increase in antibiotic consumption, unfortunately. So, and this hasn't been really the first disease that the specialists intend really to treat everybody. Chlamydia is one of those, and actually that is being debated in several countries, but the screening approach hasn't been accepted in most of the countries. But if we are looking about the prevalence, you see here is a prevalence of chlamydia, couple of percent, well below 10%. So we are not speaking about 80, 90 or whatsoever percent what we do have the prevalence of Helicobacter. So this is indeed a concern. About the cost effectiveness, indeed we do have 3 very well professional made meta-analyses on the cost effectiveness, showing that no doubt mass eradication is cost effective. And all the prominent really experts, Iris actually is coming to Riga, maybe you are going to meet her even today. Surely these are very well done cost effectiveness analysis, but there's one but. You can analyze only those data that are available, but you don't have the data available on the effects on microbiome, because the studies are not designed in the way, and actually I will come back to this in a second. So this hasn't been considered in the cost effectiveness analysis. And we were trying to go and to look into this, what we can find in respect to the costs of the resistance. And these were data a few years ago. That were experts were recommending that these were cost effectiveness experts, that they thought, okay, you have to estimate the cost of resistance and the cost of interventions to treat the resistance. And actually data are really not available on those, only on the first one. The range is terrible. So some of the authors told that the range of resistance in one patient could be in between $5 to $55,000. So this is quite a big range to put in any cost effectiveness analysis. So how to deal with this? And a recent publication from the United States has really addressed this, and probably for the first time tried to really, or succeeded to estimate. They have been using different cost models: hospitalization, inpatient costs, outpatient costs, and then also this antibiotic stewardship cost. And what have been their results? By analyzing those data, of course these are the US data, maybe here and or in other countries they might be lower, but anyhow, what they are saying that the total hidden costs attributable to each outpatient prescription is 13 USD. And each ambulatory antibiotic prescription would increase antibiotic costs by 65% if incorporated into the costs of the drugs. So meaning that this should be really added to the cost effectiveness analysis as really the drawback, as a spending on the spending part, what hasn't really been done on the cost effectiveness analysis. So I'm going to end with the hypothetical treatment algorithm that is definitely conflicting to all the different recommendations that we are currently do have in the practice, and I'm not using it in my own practice, but that would be the theoretical recommendation of the public health experts. So what to start the treatment with some treatment that doesn't cause any influence on other microbiome, non-antibiotic treatment, maybe probiotics, cranberries, green tea, whatsoever, garlic, and the effectiveness reported is quite different for these types of treatment. I believe it would be more closer to 30 or maybe below that, but even if 20% could avoid antibiotic treatment in population-based settings, that would be really the gain. If not, then probably bismuth non-antibiotic treatment could be added to this. Probably the effectiveness is similar to the previous. If not, maybe we can use amoxicillin or maybe with or without bismuth, or maybe we can use the PPIs or the PCABs, and probably these treatment regimens are coming up, and actually we are even planning to test some of them. So those are definitely much closer to the practice and with expected much higher effectiveness. And only in the case if those fail, in this case probably bismuth quadruple or alternative therapy could be given, avoiding really clarithromycin or antibiotics that should be used for treatment of other diseases. So I can leave it to discussion. I am quite sure that Jan will have something to say on this, but that is what I wanted to say from this perspective. Thank you.
thank you very much again for this excellent outline of this very specific and very interesting topic that will keep us busy in the next few decades, I probably would say. Are there any questions from the audience? I must admit I was much more skeptic. I heard this proposal of yours before that final slide, and I was a bit skeptical if we will be able to pick this up. It's again a question about evidence and how to substantiate this. But I had one of these sometimes very challenging patients just a couple of months ago who always come with a big folder of Googled information and tell you how to do your job. And she actually tried to eradicate herself with a mixture of licorice, matulity, and herbal bitters. And I was desperate to wait for the breath test to show her that she's positive and she should stop Googling, and she was H. pylori negative. So she managed to do that with her own recipe and encouraged me then to promote this among my other patients. So I think you might have a point there that with the increasing resistance rates, we need to go back to alternative methods that are not quite school medicine based and are founded in other cultures and in other evidence corners, and we need to explore these and find the way to support them with the necessary evidence. Right. If there are no further questions, I think for the sake of time, then we will need to move on with the next speaker.
Okay, next speaker on behalf of the group will be Dita Gudra, who is going to speak really on what has been managed together with the group in Sweden, and really we are very excited to see the results.
Okay, so good evening everyone. My name is Dita, and I am a scientific research assistant and also a PhD student at Latvian Biomedical Research and Study Center. And today I will introduce you with one of our recent research topics, namely OC sensor buffered samples for gut microbiome testing. So I will start with a small introduction. So human body contains about 10 times more microbial cells than human cells, although the entire microbiome accounts only for 1 to 3% of total body mass. And composition of microbiome is distinctive at different body sites, and recently there have been various research studies on focusing using gut microbiome as a biomarker for screening or discovering colorectal cancer. And most of the bacteria that inhabits our gut are non-cultivable, and thus next generation sequencing technologies gives us an insight into their community's composition, genetics, and relationship. And this can be achieved by sequencing one or more variable regions of 16S RNet gene, which is a structural component of the prokaryotic ribosome. 16S RNet gene is present in all prokaryotes, thus allowing for amplification, but the nucleotide composition is unique, thus allowing for identification. And as most of you know, fecal occult blood test is used for checking hidden blood in the stool samples, thus detecting gastrointestinal bleeding. And there are few studies that show that combination of FOBT and stool microbiome analysis seems to be more precise than FOBT alone, since in the case of gastrointestinal malignancies, also gut microbiome is altered. And in this study, we used FIT sample containers to test fecal microbiome stability within the FIT buffer. And to do so, we used Ion Torrent Personal Genome Machine and also Illumina MySeq, both of which are benchtop sequencers, and their use in microbiome research is increasing. So here's the study's design more in details. Yes, so to test stool sample stability in FIT sample containers, stool samples from 5 healthy adult individuals were acquired and immediately exposed to 16 different storage conditions. A set of samples were immediately stored at either -86 or -20 degrees, and then a set of samples were immediately frozen as ones without the buffer. And these samples were we are calling as native samples, and they're reflecting a control group. Following, samples were stored at +4 degrees, thus reflecting domestic refrigerator, at +20 degrees, reflecting room temperature, at +30 degrees, reflecting transportation within a hot climate region. And following, samples were stored for 2 days at +4 and for 2 days at +20 degrees, thus reflecting storage, sample storage at domestic refrigerator and following transportation. Yes, so here are the results of the mean DNA concentration per condition within all individuals. And as it can be seen, the yield of DNA is higher in the native samples compared to buffered ones. And our first attempt to extract DNA from these OC sensor tubes failed due to low concentration of DNA obtained. Therefore, we came up with the idea for lyophilization just to concentrate the material. And in this manner, we were able to increase the yield of DNA up to 30 times. And yes, and when we are, and it also can be notable that keeping samples in a liquid state for a longer period of time, the yield of DNA increases when compared to day 1. And here are the sequencing results. Here are samples, all the samples that were sequenced by ion-torrid personal genome machine. And as it can be seen, dominating orders are Clostridiales, Bacteroidales, and the green ones are Lactobacilliales. And if we consider the individuals, then it can be observed that relative abundance of each bacterial order varies between individuals, and that individual 1 and 2, as well as 4 and 5, are more similar than others. We also calculated Shannon Diversity Index, and Shannon Diversity Index is a measurement used in microbiome studies to describe a sample diversity within the sample. And here it can be seen that samples without fit and samples within fit immediately frozen to -86 or -20 degrees or stored for a few days at +4 degrees display a similar mean value of Shannon index. And these results indicate that differences in these results start to appear when samples are stored for a longer period of time, along with the increase of temperature. Yes, so when comparing these results between the two sequencing platforms, there is a significant difference in the terms of diversity, and this is probably due to different amount of data that was obtained from each platform. So more specifically, with ion-torrid personal genome machine, we obtained 10 times more sequences when compared to Illumina, and most likely these differences in the amount of data also appears here. And when analyzing the data that came from MySeq data, we found that when storing samples in fit sample containers for 7 days at 30 degrees, they did differ significantly from the native samples, from samples stored in fit buffer at 4 degrees for 1 and 2 days, as well as they differed from samples stored in fit buffer stored at 20 degrees for 1 day. We also calculated beta diversity metrics, and beta diversity means between sample diversity. So according to unweighted unifracs, samples collected from each individual tended to cluster together, and thus suggesting that biological effect outweighs the effect of sequencing technology. As it is for weighted unifrac, no pattern of clustering according to individuals was observed. sorry, but it was, we can notice that samples from, sample aliquots from each storage condition tended to cluster near. And according to those results, it's possible that the samples were undergoing small yet specific alterations in their microbial DNA composition. So here are relative abundances of bacterial orders by storage conditions from both sequencing platforms. And to evaluate the uniformity of our native samples, we mutually compared them. And according to analysis, bacterial orders of native samples did not differ significantly, thus serving as an appropriate reference group. We also performed analysis at the level of O2s across all taxonomical levels without application of any cutoff. Maybe I will a little bit define here what is O2. So it's operational taxonomical unit, or more simply, just taxonomical unit. And in this manner, we were unable to identify any specific, significant difference between different storage conditions regardless of the sequencing platform used. However, we noticed that there might be some microbial patterns affected by storage conditions, and thus we noticed that there were bacteria that tended to increase over time or decrease over time. And taking a look closer, we found that abundance for most of the gram-negative bacteria tended to decrease over time, while for most of the gram-positive bacteria, it tended to increase over time. And this conjecture might be explained by the presence of feed buffer, which most likely possesses lytic characteristics during the long-term storage, thus inducing inaccurate results regarding to the relationship of gram-positive and gram-negative bacteria. And to conclude on this topic, so for OC sensor tubes, it seems to be, the lyophilization seems to be essential to extract sufficient amount of DNA. Also, microbial diversity rates tend to decrease during prolonged term of storage at higher temperatures. Bacterial community structures and taxonomical distribution did not change significantly across different storage conditions. However, we noticed the shift in these bacterial patterns. And in overall, this study supports the use of feed sample containers for storage and microbiome studies, and the storage for up to a week, just to be safe. And yes, so we took into account our knowledge from that practical research when planning new projects, and now we have an ongoing project where we are assessing the effect of pylori eradication on gut microbiome, and it shall be finished quite soon. So soon we will see the first results, and then we will continue with studying ESBL genes, since these genes are known to be responsible for developing the resistance against antibiotics. And there is also a project in preparation which will involve samples from a G-star population. The idea here is very similar to the already ongoing, except that there will be tested different eradication therapies. In this project, we are looking at one eradication strategy, which, as I know, which is the first-line therapy. But yeah, here will be two different ones. And yes, and I think that would be all. So thank you for your attention.
Any questions, comments? No questions, so thank you indeed. And then now we are proceeding immediately to the last presentation, and actually we are really happy that BGI group is settling here in Latvia and trying to do big work there. So please, the floor is yours.
Hello, I think this is the last presentation, so I'll keep it quick. So my name is Arthur. I work in the BGI, and today I would like to be honored to share our metagenomics platforms in BGI, as well as a service and as a research platform. So some background about, if not everybody knows, what metagenomics is. Metagenomics is actually the whole microbial community which inside our body, which can be viewed as a microbial organs that placed into your host organs. So in this way, it is a second genome besides our human genome, if we talk about us. And based on research we have done back 10 years ago, actually there are 100 times more of the number of genes in this second genome. And since it is widely exists in the gut, it has very crucial functions related to either digestion, development of immune system, and others. And also thinking about metagenomics, typically speaking, we are talking about 3 areas that you may have seen in the last presentation. One thing is the 16S ribosome DNA sequencing. The other one is the whole genome of the microbe, we call it metagenome, and the whole total RNA level, which is the metatranscriptome that we are talking about. So this area of study started actually from this paper published in 2010 on Nature, which is a proof of principle metagenomic study paper. BGI is actually one of the authors in this paper and contribute a lot on the methodology part, especially on the bioinformatics. It sets up a very fundamental way about this area to say, okay, what tools to use, what bioinformatics analysis pipeline should be there, and what can we find from metagenomic study. And the very first paper used actually 124 individuals and found 3.3 million gut bacterial genes in it. So what it looks like? It looks like in this way. We get samples, we get a DNA extraction, and we fragment it. And then using the shotgun sequencing, which is next generation sequencing, and different platforms. But the idea is to get the base pair data from the sequencing data, and then overlapping the fragment into large contours, and by different informatics tools, you can either do taxonomic profiling, virulence factor analysis, and functional profiling, and combine these 3 together, you have a better idea how this group of microbes would actually function in your host or in the environment. That has been done for 8 years, and lots of papers has used this paper. But recent years, I think start from 2015, metagenomics is actually become more and more attentionable in disease research area. So that's why what is actually widely used in BGI research today is metagenome-wide association studies, MVAS. This is actually, you can tell, is modeled from GWAS, which is genome-wide association study. The GWAS study is actually used for population study to find the driven mutations in one certain population, which relate to its factors and key phenotypes. And MVAS study is the same. As we already know, by metagenome, you can map in the genome of the novel organisms to know, okay, it's a new organ, what is there? And also you can finish in the genomes of a known organism by comparing with the reference gene catalogs. But by MVAS study, you can actually compare between multiple samples from the cohort and to know what is actually associated with the disease of interest. So that's the beauty of this methodology. And the next slide, I'll show you how the general steps of carrying out MVAS. But here is 4 things you should should really pay attention to when you design and carry out MVAS. The first thing is how to get the data. There are different sequencing platforms, different sequencing strategies, and also every sequencing platform has its own advantage and disadvantage comparing with the data. So thinking about what you want to get or what you want to use in the analysis stages. And then the also crucial thing is the microbial reference gene catalogs that you need to use when you are doing analysis. Because as far as I know, one of the most high quality of these catalogs are from the gut microbes. Others, like from the skin and from oil, are still under development. So that gives you some of the disadvantage if you want to take samples from there. And also try to think about taxonomy from metagenomic data, and as well as to control phenotypes in the MVAS, so to avoid unnecessary things. So here is the picture that example of using MVAS in disease. This is I pick out from this review paper published on 2016 on Nature Reviews. It has 7 steps, but in general it can be divided into before experiment, analyze, and validation, the 4 stages. I think the most crucial one is the cohort choose, to know your aim of the study, what you are really looking into by MVAS. Either you are comparing a healthy group or a sick group, like the people has with or without gastric cancer, as an example. Or it is the same of the group of people, but with drug treatment before or after status. You can also compare with a group of people and with the natural going of their development. So from an epidemic level, to see how they gradually develop into different type of disease. And also you can see a certain type of people with the same disease and how, with the progression of the disease, how their management changed and shifted during this process. So knowing your purpose of your study of MVAS helps you to choose the correct cohort in return. And then it is a sample collection, as we have already discussed. The catalog, the reference gene catalogs differs and has different quality. So choose from different samples based on your needs is actually quite important here. And then it is the lab work part, which using different platforms. We have Illuminas, we have LifeTex, we have BGIs, as well as the new player Quangens. They all have different strategies when it comes to the chemical part. So they have different ways to build up their library, which affects the data generated from the sequencer. But this would then affect the abundancy study, annotation, and assemble into context when we're using the NH tools. But once we have do that, and we have a group of people from a group of data from different cohort, we compare and link with the phenotypes we have. We may have some identification with the disease on the metagenomic level or metatranscription level, and then how to verify that. You can either do a larger or wider MVAS study, choosing more of the participants into study and compare to verify your results. Or you can also do animal tests that to feed the microbes and to see how it in return could develop into disease. So this is a typical way of MVAS study, and lots of disease has been studied by using this method, like type 2 diabetes, obesity, and several others, which I think this paper has several, you can find more of the scientific results with this disease. Here's another example with adenoma and carcinoma. There are 156 facial samples from different stages of this disease, and then they do the meta-sequencing and to do using the metagenomic linkage groups method to see how it is associated with the disease at different stage. The metagenomic linkage groups actually means that it is physically linked in the host, but not independently distributed. And by looking at the MLGs, we found this diagnostic value of the facial microbes for colorectal cancer. And this can actually be driven into later clinical applications in daily clinical lives. So we think this is a good example of using MBUS to find something, the linkage to the disease, and then can turn into applications on industrial levels. And then something about what BGI can offer on metagenomics. We actually have 3 platforms that can do metagenomics, and here are them. In the middle one, the MGISAC 200 is with small capacity, but is very flexible with individual labs, so that you can perform the metagenome and do it at very low cost. The BGISAC 500 and MGISAC 2000 is actually designed for more centralized lab, like big facilities, so that they can do the samples in large portion. And you may ask, okay, how you have a platform, but Illumina is a big player, is a big brother here. What's your comparison with them? We have a paper published in last December on GigaScience about using the CPAS method, which is our chemical methods, to compare with on metagenomics. And we compare the data from BGISAC 500 with 2 platforms from Illumina. The paper is open access, so you can easily get them from GigaScience webpage. Within 20 samples, and the quality control looks very well. The Q30 is above 90%, which is similar to Illumina's. I only pick one photo because I think the rest of them are too complicated for me to explain. But thinking about the killer ratio and the mapping ratio and the unique mapping ratio, they are very identical with Illumina's platform. And it is able to do MS. So we think we offer an alternative option compared with Illumina's platform. So that's what I would like to share with you. And in short, I think BGI is setting up a lab here in Riga, and we do hope that this lab, the facility here, would help the guys on the site to have a better research and better outcomes in the future. Thank you.
Thank you. Any questions? No questions? So then we do have some time left for the discussion. Anybody would like to discuss those issues?
I would just like to pick up Geoffrey's comment from earlier that we really need, and I think these meetings here are a good chance for that, to collaborate, and not only collaborate between different research groups, but also with the different levels of patients, healthcare providers in the community setting, in the academic setting, and we should get rid, and I think we're all on a good way for that, of the old anxiety that someone might steal our ideas, or we don't have the hold on a certain paper or project, and really work together to generate these projects with all the elements to see that the quality of the research gets better, with the aim that the quality of the patient care gets better as the main endpoint. And I think this is what we should work on, and I think this is what we're here for.
Thank you. And if there's anybody who wants really to discuss, then actually we are not finishing yet the program here, but we have the next 2 items in the program. First thing is we will be taken on an excursion here in this building that is actually a library building. And then we do have also the coffee that will be served downstairs. So please, I think that probably we can leave the coats here, but maybe I'm wrong. Let's see what they are saying. But let's go downstairs and continue. But I would like to thank everybody that has been participating and speaking. Thank you.